Okay, so we have seen how one can come up with something called the Cauchy-Schwarz inequality. We first looked at it using two-dimensional vectors and three-dimensional vectors and so on, and then we saw that this can be generalized to arbitrary vectors in the more the abstract vectors from a linear vector space. And so there's another inequality which is called the triangle inequality, which is also possible whenever you have an inner product, right? So it's very we're going to derive this for abstract vectors using the Cauchy-Schwarz inequality in this lecture. Okay, what is the triangle inequality? It's simply the statement that if there are in Euclidean geometry, right? If you're going from a point A to a point C, then the shortest distance between A and C is if you take the straight line path, right? If you go to C via some other point B, right? So you go from A to B and then go from B to C, then necessarily AB plus BC can never be smaller than the direct line AC, right? So it seems like a completely obvious statement, but it is it has its own power, and it can be made abstract and it can be extended to abstract vectors, which is the subject of this lecture, right? So we can state the same fact with vectors like here, right? So now let's see how we can extend this to abstract vectors from a linear vector space. So let's start with some two vectors A and B drawn from a linear vector space. And first of all, there is this notion of a distance that we can define between any two vectors in a linear vector space which has an inner product. The moment you have an inner product, so that's one reason why the inner product is important. A linear vector space that is endowed with an inner product automatically becomes what is called a metric space, which means that it simply means that there is a well-defined notion of a distance between any 2 points in this space, right? So in general, there are multiple ways of defining distance between 2 points. It's not unique. It's just like the notion of an inner product itself is not unique. It must satisfy certain properties. Likewise, the notion of a distance is also not in general unique, right? But let's not go into like a formal definition of distance, but let me just tell you that one essential requirement for a distance to be a distance is that it must satisfy triangle inequality, right? So if you take any 3 points and then you compute the distances according to the prescription given to you, then triangle inequality must hold, right? So this is like a requirement. So let's see how the triangle inequality works out for what is the most natural way of defining distance on a linear vector space where a norm is defined, where an inner product is defined. So think of these two vectors A and B. So just simply subtract these two vectors and create another vector. The difference of two vectors is also a vector, right? Because it's a linear vector space. Linear combination of vectors also belongs to the same vector space. And then find the norm of the difference between these two vectors. So it doesn't matter whether you do A minus B or B minus A. You're going to take the norm of this quantity, which is just simply defined as the inner product of the difference of these vectors with itself, and then you have to take a square root of this, right? And the square root is always something that you can do because it's a real number and it's a positive number, right? So this is all encoded into the notion of an inner product already. So it's completely well defined. And now we will show how we can use the Cauchy-Schwarz inequality to prove that this distance will satisfy the triangle inequality, and therefore this becomes what is called a metric space, right? Okay, so let's see how this works out. So the goal is to show that if there are any three vectors A, B and C, the distance between A and B plus the distance between B and C must necessarily be greater than or equal to the distance between A and C. That's the goal, right? So let's start with some notation. So we'll define the vector alpha as the difference of these vectors a and c, a minus c. The vector beta is the difference of the vectors a and b, so a minus b, and then gamma is vector b minus vector c. So then we clearly have alpha is equal to beta plus gamma, right? So it comes from all these cancellation. Minus c will cancel with plus c, and then minus b will cancel with plus b, and you can quickly verify that you will just have alpha is equal to beta plus gamma is something that you can check. It's evident from the definition. Now we will take an inner product of of each quantity of this equation, both on the left hand side and on the right hand side. So alpha with alpha, and then beta plus gamma with beta plus gamma on the right hand side. So if you take the inner product, then you have inner product of alpha with alpha is equal to inner product of beta with beta plus inner product of gamma with gamma plus inner product of beta with gamma plus inner product of gamma with beta on the right hand side, right? So which we can write it as beta beta plus gamma gamma plus 2 times real part of beta with gamma. So how does this come about? This comes about just from the fact that the inner product of a vector beta with gamma is equal to the inner product of gamma with beta conjugate, right? Gamma beta whole star. So, and then you can verify that if you take any complex number and add to it its complex conjugate, it's the same as 2 times the real part of the complex number. That's all that's going on here. Now we use property of complex numbers, if you wish. The real part of a complex number is necessarily going to be less than or equal to the modulus of this complex number. So in place of 2 times real of beta gamma, we will write it as less than or equal to 2 times complex the modulus of this complex number, inner product of beta with gamma, right? So where all I have used is the fact that if you have any 2 real numbers, the real part is a real number and the imaginary part is a real number. If I think of it as x and y, then surely x must be less than or equal to square root of x squared plus y squared for any 2 real numbers x and y, right? Because the right hand side, if at all you're doing something, you're adding to it, or if y is 0, then you're going to get back x itself. So you can never, by doing the procedure on the right hand side, you can never remove something from x. You're only adding, if at all, right? So this is an obvious inequality. So we have used that already. Now we are ready to invoke the Cauchy-Schwarz inequality, right? So we already have this inner product of beta gamma, modulus of inner product of beta gamma. So we know that the modulus of beta with gamma, the modulus of the squared is going to be less than or equal to the modulus of beta, the inner product of beta with itself times the modulus of gamma with itself, the inner product of gamma with itself. So that's the Cauchy-Schwarz inequality. So if you just plug this in, so we'll put it in with the square roots. So then we have inner product of alpha with alpha is less than or equal to inner product of beta with beta plus inner product of gamma with gamma plus 2 times square root of the modulus of beta with beta times the modulus of gamma with gamma, right? So now it's in a form which you can complete the squares and simply write the right hand side as the square root of beta with beta plus square root of gamma with gamma, right? So therefore, and then if I take square roots on both sides, I'm basically done now. We have managed to show that square root of alpha alpha is less than or equal to square root of beta beta plus square root of gamma gamma, right? Which is the same as saying rho of a times c, rho of a comma c. So the distance between a and c necessarily is less than or equal to the sum of the distances a to b and b to c, right? So this is the triangle inequality. So which is the inequality we set out to prove, and therefore this is this notion of a distance defined like here is a legitimate notion. There are 2 other properties which are obvious, like the distance between a point and itself is 0 according to this definition and so on. So given that triangle inequality holds, this space becomes a metric space. So every linear vector space endowed with an inner product definition. A well-defined inner product makes it a metric space. So that's what this lecture was all about. Thank you.